The power rule tells us that the derivative of a function x to the n is nx to the n minus 1. To master this rule takes some practice. And to do that, I'm going to walk you through all 20 of these progressively more challenging power rule problems. In each case, we're just taking the derivative, though you can see I use some different notation just to mix it up. Once we're done all 20 of these, I'll give you some bonus problems for the road. Let's get into it. Beginning with problem 1, we're given that f of x equals x squared. We want to find the derivative f prime of x. Remember, the power rule just says if f of x equals x to the n, in this case n equals 2, then f prime of x, the derivative, is n times x to the power of n minus 1. So we bring that exponent, that n, down as a factor, and then we reduce the exponent by 1. The exponent was 2, we subtract 1 from it, and so now we're just left with 2x to the power of 1, and of course we don't need to write a power of 1, so we find that the derivative is just 2x. It's as easy as that. If f of x is x cubed, then f prime of x is bring down the exponent as a factor, reduce the exponent by 1, 3x to the power of 2. In the first two problems, we were given a function f and we wrote the derivative f prime. In problem 3, we're just asked to find the derivative of x to the 4. In this case, n, the exponent, equals 4. So what's the derivative of x to the 4? Well, by the power rule, we need to bring that exponent down as a factor and then reduce the exponent by 1. So the derivative of x to the 4 is 4 times x to the power of 4 minus 1. Of course, that's just 4x to the power of 3. I'm sure you're getting the hang of it now. Derivative of x to the power of 7, n equals 7. To take the derivative, bring that power down as a factor, and then reduce the power by 1. So that power of 7 becomes a power of 6. The derivative is 7x to the power of 6. Now what about the derivative of x? This should be the easiest example so far, but some people can be a little sketched out by it. What's the power of x here? There isn't a power written, so the implied power is just 1. The power rule applies as usual. Bring that exponent of 1 down as a factor, and then reduce the exponent by 1. So it's 1 times x to the power of 0. But anything to the power of 0 is 1. So this is equal to 1 times 1, which of course is just equal to 1. Hopefully that makes sense, because remember, the derivative of a function is the function's slope, and you probably remember from your algebra classes that y equals x is a line with a slope of 1. But again, if you want to think about this in terms of the power rule, the exponent is 1, we bring that down as a factor, and then reduce the exponent of 1 by 1, which makes it 0, and so in total, this is just equal to 1. What about the derivative of a constant, like the derivative of 2? Well, if you know what the derivative is, it's the rate of change, so certainly this should equal 0. It's a constant, it's not changing, so the derivative is 0. If we want to apply the power rule, though, then we need to ask what power of x is this? Well, 2 is the same as 2x to the power of 0, since x to the 0 is just 1. Then we could apply the power rule if we wanted to. We could take that exponent of 0 down in front as a factor, so it's 0 times 2x to the 0 minus 1. We have to reduce the exponent by 1, and 2x to the 0 minus 1 doesn't really matter what that is because it's getting multiplied by 0. So what's the answer? It's 0. In general, what's the derivative of any constant c? Constants don't change, so the derivative of any constant is 0. Again, by the same logic as before, you could use the power rule if you wanted to, though it's certainly overkill here. We would drop the exponent down as a factor, then that's 0 times c x to the negative 1, because we have to reduce the power of 0 by 1, and 0 times anything is 0, so there you go. All right, let's move on to fractions, the derivative of 1 over x. The power rule also applies here, because what is 1 over x? If we were to just write it as a power of x, so let's just rewrite the expression, 1 over x is the same as x to the power of negative 1, because a negative power just sort of flips the base. X to the negative 1 is 1 over x. Once we write it like this, it's evident that we can use the power rule. Bring the exponent in front, the exponent is negative 1, and then reduce the exponent by 1. So this becomes negative 1 times x to the power of negative 1 minus 1, which is negative 2. And if you want to rewrite this so that the exponent is positive, which often we do, we can just put the x in the denominator. In the same way that x to the negative 1 is 1 over x to the negative 2 is 1 over x squared. However, in this case, our numerator will be negative 1 because that negative that we have in front. So what's the derivative of 1 over x? Well, we can rewrite it as x to the negative 1 and then apply the power rule to find negative 1 over x squared as the answer. What about the derivative of 1 over x cubed? This is the same exact idea. 1 over x cubed is the same as x to what power? Negative 3, right? The negative sends it to the denominator, and it needs an exponent of 3. So x to the negative 3. Then we apply the power rule. Bring the exponent down in front as a factor, and then reduce the exponent by 1. So it becomes negative 3x to the negative 3 minus 1, which is x to the negative 4. And again, if you're inclined to write this so that there isn't a negative exponent, leave that negative 3 factor up in the numerator, and then write x to the negative 4 in the denominator as x to the positive 4. One more basic example like this, g of x equals 1 over x to the 4. So what is g prime of x? Well, 1 over x to the 4 is the same as x to the negative 4. So we can take the derivative using the power rule, bring that exponent of negative 4 out front as a factor, and then reduce the exponent by 1. Negative 4 minus 1, of course, is negative 5. So this derivative is negative 4 times x to the power of negative 5. And pro tip, if you're doing some more math with these derivatives, like plugging in x values, remember that it's just the x value that's receiving these powers. Even back to this first example with just 1 over x, the negative 1 is not receiving the power. It's only the x that is receiving the power. Be careful when you're plugging stuff into these. All right, we're moving on to this second set of 10 examples. They're getting a little harder. Let's get into it. The power rule is great because it works with any exponent. 0, 1, negative 1, even if it's a fraction, it's no problem. What about h of x equals x to the 1/2? Well, it's worth pointing out that this is the same as the square root of x, but either way, we can just take the derivative with the power rule right off the bat. H prime, the derivative of h, well, we just apply the power rule to x to the 1/2. Bring the exponent of 1/2 out as a factor, and then reduce the exponent of 1/2 by 1. Now 1/2 minus 1 is negative 1/2, so the derivative is 1/2 x to the negative 1/2. As before, we can write this in the denominator with a positive exponent. Since we have a factor of 1/2 out front, that's the same as a 2 in the denominator, and then we also have our x to the 1/2 in the denominator. Or, like I said before, x to the 1/2 is the same as root x, so we could write this as 1 over 2 root x, and that's the derivative of x to the 1/2, which, like I said, is root x. Even if it's a nastier fraction, like 7/8, still no problem. By the way, remember that x to the 7/8 is the same as the 8th root of x to the 7. It's easier when we start here because we can just apply the power rule from the jump, but we will soon do examples where we start with the radical and then have to rewrite it with the exponent. For now though, we get the exponent right from the beginning. So we want the derivative of x to the 7/8. Just take the derivative using the power rule. Bring the exponent of 7 over 8 out front, and then reduce the exponent of 7 over 8 by 1. Instead of writing minus 1, to help me do the math, I'm just going to write minus 8 over 8. That's the same as minus 1, but of course it's got the same denominator as my exponent, so it's easier to do. This is equal to 7 over 8, and then x to what power? Well, 7 over 8 minus 8 over 8 is negative 1/8. We can then rewrite this to get rid of the negative exponent. There is a 7 in the numerator because of this factor of 7/8, and the 8 is in the denominator, and then x is in the denominator with now a positive power of 1 over 8. Or if you prefer, instead of writing a power of 1 over 8, we could write the 8th root of x. All right, here's problem 13. We're starting with the radical expression. Let's begin by rewriting it as a rational exponent, and then we can apply the power rule. The 5th root is the same as a power of 1/5. So this is the derivative of x cubed to the power of 1/5, which of course by our exponent rules is the same as x to the power of 3/5. You can just multiply the exponents together. So we're taking the derivative of x to the power of 3/5, and we can do that using the power rule. Bring the exponent of 3/5 down in front as a factor, and then reduce the exponent of 3/5 by 1. Instead of writing -1 for ease of the operation, I'll write -5 over 5. This is 3 over 5 times x to the power of 3/5 minus 5/5 is negative 2/5. Then we can rewrite this to get rid of the negative exponent. We have a 3 in the numerator, 5 in the denominator, with an x to the power of what's now positive 2/5. I was a little overzealous with that fraction bar. Let me shrink this down a little bit. And there you go. That's the derivative of the 5th root of x cubed, 3 over 5x to the 2/5. Let's move on to example 14. We can have fractions and radicals all in one. It's great. This is the derivative of 1 over the square root of x. Remember, having x in the denominator is just like a negative power. So 1 over the square root of x, that's the same as, well, 1 over x to the 1/2. But since the x is in the denominator, that's the same as x to the negative half, written like that. Once more, the square root is a power of 1/2, but because this is in the denominator, it's actually a power of negative half if we want to write it without the fraction. Once we write it like that, we can take the derivative using the power rule. Bring the exponent down in front as a factor, so negative 1/2, multiplied by x to the power of negative 1/2 minus 1. I'll write minus 1 as 2 over 2. So this is negative 1/2 multiplied by x to the power of negative 1/2 minus 2/2 is negative 3/2. We can then rewrite this to get rid of the negative exponent. We have a negative 1 in the numerator. In the denominator, we have this factor of 2, and then we'll write it as the square root because we have a power of 3/2, so square root, but then the 3 is the exponent of x. So there you go. The power of 3/2 is the same as the square root of x cubed. And because it's negative, we put it in the denominator. Remember, when you have a rational exponent, the denominator tells you the index of the radical. In this case, that's 2. It's a square root. And the numerator of the exponent tells you the power of x. So that's why we have x to the power of 3. Number 15, 1 over the cube root of x squared. We're going to find the derivative of this, but first we'll have to rewrite it so it's just x to some power. For starters, we can actually just get rid of the fraction right off the bat. We can rewrite this as the cube root of x to the negative 2 now that we've gotten rid of the fraction. A cube root is a radical with an index of 3, so we can turn that into an exponent of 1/3. So this is the same as x to the negative 2 to the power of 1/3. And then like we did before, all we have to do is multiply the exponents together. This is x to the power of negative 2/3. Now that's just a rewritten form of a of x, and that makes it easy to find a prime using the power rule. To take the derivative of this, we just need to bring the exponent in front as a factor, so negative 2/3, multiplied by x, and then we'll subtract 1 from the exponent. The exponent is negative 2/3, so we'll subtract 3/3. This is equal to negative 2/3 x to the power of negative 5/3. We can then rewrite this to get rid of the negative exponent. We have a numerator of negative 2 and a denominator of 3 multiplied by the cube root of x to the power of 5, or just x to the power 5/3 if you prefer. Again, the denominator of the fractional exponent tells us the index of the root, it's a cube root, and then the numerator tells us the power, x to the 5. Next is 16. This is a pretty similar example, the derivative of 1 over the 5th root of x to the negative 3rd. We begin very much like the previous problem. Let's just get rid of the fraction. So this is the same as the 5th root of, the power was negative 3, but since we've got rid of the fraction, it's now x to the positive 3. We've moved it up to the numerator, so the sign of the exponent flips. Since it was negative, now the exponent is positive. Now a 5th root is the same as an exponent of 1/5. So this is the derivative of x to the power of 3 to the power of a 5th, which is just x to the power of 3/5. Now we can use the power rule. Bring the exponent of 3/5 out front as a factor, and then subtract 1 from the exponent, so minus 5 over 5. 3/5 minus 5/5 is negative 2/5. So this is 3/5 x to the negative 2/5. We can rewrite this to get rid of the negative exponent. We have a numerator of 3, and then a denominator of 5x to the positive 2/5. Next, the derivative of 7 over the 8th root of x to the 4th. The 7's just going to hang out this whole time as a factor. It's not going to have a huge impact on things. Just keep that 7 there. So let's rewrite this with an exponent and no fraction. We can move the x to the 4th up to the numerator by flipping the sign of the exponent. So this is the derivative of 7. Like I said, don't ignore your 7, just leave it there. It's not going to cause any problems. Then we have the 8th root of x now to the negative 4 because we moved it to the numerator. An 8th root, though, is the same as an exponent of 1 over 8. So this is the derivative of 7 multiplied by x to the negative 4th to the power of 1/8. That's what the 8th root is as an exponent. Now we can multiply those exponents together. If you want, you could also take the 7 out of the derivative. The derivative of 7 times a thing is the same as 7 times the derivative, but I don't care. I'm just going to leave the 7 in there. This is the derivative of 7 times, multiply those exponents. Negative 4 times 1 over 8 is negative 4 over 8, which is actually negative 1/2. All right, now we can use the power rule. We need to bring the exponent of negative 1/2 down as a factor. So this is negative 1/2 multiplied by 7 multiplied by x to the negative 1/2 minus 1. Minus 1 is the same as minus 2 over 2. So what's this? Well, negative 1/2 times 7 is negative 7/2, and then the exponent is negative 1/2 minus 2/2. That's minus 3/2. Finally, we can rewrite this to get rid of the negative exponent. Our numerator is negative 7. Our denominator is 2x to the power of 3 over 2. There's 17 one more time if you wanted to look through it. Final answer, negative 7 over 2x to the 3/2. 3 to go. Let's move on to 18. This is 4x squared divided by the square root of x to the 10. We're going to have to use some exponent laws here. Let's begin by trying to rewrite this so it's just x to a power with a constant hanging out if necessary. As we've been doing, we can get rid of the denominator by just flipping the power. So where we did have the square root of x to the 10 in the denominator, we can bring it up to the numerator if we flip the power of 10 to a negative 10. So there we go, 4x squared times the square root of x to the negative 10. But this square root is the same as a power of 1/2. So this is the derivative of 4x squared multiplied by x to the negative 10 to the power of 1/2. We can bring the 4 out of the derivative if we want. I'll do it this time just for variety. So this is 4 times the derivative of x squared times, multiply those exponents. Negative 10 times 1/2 is negative 5. So x squared times x to the negative 5. Hopefully you remember your exponent rules. This is 4 times the derivative of, since these guys have the same base, it's x and x, all we have to do is add the exponents together. So 2 plus negative 5, which is negative 3. Now we can use the power rule. We'll want to bring that negative 3 out as a factor, so 4 times negative 3, and then reduce that power by 1. Negative 3 minus 1 is negative 4, so I'll just write that. Finally, what's our answer? Well, 4 times negative 3 is negative 12, and then the x to the negative 4, I'll write in the denominator with a positive 4 power. All right, problem 19. This one's a little bit of a break. 4x to the power of pi. Don't be intimidated by the pi. This works the same as always. Bring the exponent out as a factor, so 4 pi, x to the power of, reduce the exponent by 1. So now the exponent is pi minus 1. And there's no way to simplify this answer, although I could write that pi a little nicer. So there we go. 4 pi x to the pi minus 1. Not a problem at all. Finally, number 20, g of x equals e times the square root of 1 over the cube root of x. All right, well, let's rewrite this so it's just x to a power, and then we'll find what g prime is. This is going to be e multiplied by the square root of, let's move that cube root of x to the numerator. A cube root is the same as a power of 1/3. So this is 1 over x to the third. So if I want to move that x to the numerator, I'm going to have to make it x to the negative 1/3. So there we go. We just brought the cube root of x up to the numerator by making the power negative 1/3. Now, the square root is the same as a power of 1/2. So this is e multiplied by x to the power of negative third to the power of 1/2. Multiply those exponents together. This is e times x to the power of negative 1/6, and now we can take the derivative using the power rule. So what is g prime of x? Well, we've got to bring this exponent down as a factor, so negative 1/6 times e, and then reduce the exponent by 1. Negative 1/6 minus 6/6 is negative 7/6. So there we go, and we can rewrite this to get rid of the negative exponent. Our answer is going to be a numerator of negative e, and then a denominator of 6 times x to the power of 7 over 6. There you go. Hopefully not as bad as you were thinking. Again, a cube root of x is the same as a power of a third, so we were able to move it to the numerator by making it a negative third, then just apply our exponent laws, and then finally the power rule. Here's one more look at all of the examples and our written out solutions in case you wanted to take another look at them. As if that wasn't enough, here's some more problems. There are 20 more problems here that get even harder. You can see 10 of them for free and give them a try. If you want to support the channel, become a channel member and you can access another video where we solve all 20 of these additional challenge problems. And there's a link in the description you can check out to see all the exclusive members content for calculus. Hope this was helpful. Let me know in the comments if you have any questions, and thank you very much for watching.
Myself up for an instant. What's the law? It's regular. I regulate my integrity. I'm a secular anesthetic from my